Okay, hello everyone. From this class, we are going to start to discuss about application of Laplace transform on electric circuits. In this class, particularly, we are going to discuss RL circuit or to solve the differential equation of RL circuit. This is the differential equation of RL circuit. To solve this differential equation means we have to find out the instantaneous current. In this lecture or video, we are going to discuss about RL circuit. Next class we are going to discuss RC circuit. Then next class we are going to discuss LCR circuit. Okay, so let's start to discuss to simplify or to solve the RL circuit using Laplace transform. So here the RL resistance and inductor are connected with a series and a EMF or applied voltage has been connected, and this is your key, and when key will be closed for some time the current will be flow in the circuit. Okay, so consider a RL circuit which is connected with a source EMF E as shown in figure. Here R is your resistance and L is your inductance. From figure it will be observed that when key will be closed, then the voltage drop across R and L, and the voltage dropped across R and L are we know that voltage drop across the R will be IR, and voltage drop across the L will be L into di by dt. Okay, so here I have to just modify it. From the figure it will be observed that when key will be closed, current I will be flow. Here I have to just current I will start to flow start to flow start to flow. Then the voltages drop across the R and L are this and this respectively. Here I is the current flow in the circuit when key is closed. Here I written also, and here I is the function of t obviously. So for a time, if the key will be closed, for that time of period I will be uh, current will flow in the circuit. Okay, that means with time current will be changed in this circuit because L is there. L will be store the magnetic energy, and again when the battery will be or key will be disconnect, that energy will be lost by the inductor, that we know. So here current whatever is going to be flow inside this circuit when key will be closed, that is the function of t. These voltages are dropped across R and L is instantaneous. That means when t tends to 0, t tends to 0, that means when when key closed, at that moment only voltage drop we can found across R and L. Okay, so hence at t tends to 0 the key is connected. That means at instantaneous, at when t tends to 0, that means when key is connected, by applying KVL, that means Kirchhoff's voltage law, we can get the voltage drop across R IR plus voltage drop across L is your L into di by dt will be applied voltage, will be equal to applied voltage. Let this is your equation number 1. By solving equation number 1 using Laplace transform, the instantaneous current, that means I, which is the function of t, can be evaluated. So here the given differential equation is your L di by dt plus IR equal to E. Let this is your equation number 1. Same thing it has been written. Now we have to apply the Laplace transform both the side on the equation number 1. Laplace transform of this one, Laplace transform of this one, Laplace transform of E. Here you can see this format. L is your Laplace transform and this is your capital L, your inductance. Okay, d into here L taken outside, and we know that this is the Laplace transform of first order derivative, so it will be s into Laplace transform of I, which is the function of t, minus I at t equal to 0, plus r taken outside, Laplace transform of it equal to Laplace transform of E will be written as 0 to infinity e to the minus st into E into dt. That we know in general if we have a function f of t, then Laplace transform of f of t is nothing but 0 to infinity e to the minus st into f of t into dt. So here Laplace transform of e will be e to the 0 to infinity, sorry, 0 to infinity e to the minus st into e into dt. So here we just substituted, instead of Laplace transform of it equal to I bar, then above equation, and at the meantime we have to also consider the boundary conditions. What is the boundary condition? Here I written, see, first we have to substitute this one, instead of Laplace transform of t equal to I bar. So this s into this one will be I bar minus, here you can see, I will be equal to 0 when t equal to 0. T equal to 0 means, as t equal to 0, when I will be equal to 0 when t equal to 0 is the boundary condition. That means when t 0, that means when key not connected, current inside the circuit will be 0. So instantaneously when the key connected, at that moment current we can found in the circuit. But when t equal to 0, t equal to 0, that means key is not connected, t key is not closed. But when t key closed, t not equal to 0, that we can say t tends to 0, t tends to 0 when key is closed. But t equal to 0 is the boundary condition when key not closed. Okay, so if t equal to 0, at that time I inside the circuit will be 0. So here I at t equal to 0 will be equal to 0. Okay, so this side has been written same. Here you can see nothing has been changed. So let this is your equation number 2. Let this is your equation number 2. Now key is closed for a certain time. Suppose we are going to close this key for a certain time, that is your t equal to a, then opened for a short time period, key has been closed, that time is your a, and then opened. Then that means voltage connected to this circuit for t equal to a time, t equal to a time, then open. So that then corresponding EMF, whatever is going to be applied, that can be represented mathematically like this. E will be equal to E when the time in between 0 to a, and will be 0 when t greater than a. That means in between time the EMF has been connected with this circuit. This EMF will be connected with this circuit. That means key will be connected for time period up to a. Then after key opened, then after t, after a, key opened, so EMF obviously will be disconnected, will be 0. Now equation number 2, here you can see equation number 2 will be written as L. Here I bar is there, I bar taken common, ls plus r equal to, I bar taken common, ls plus r equal to, here this one 0 to infinity will be segregated as, here with respect to time integration is there, so time segregated as 0 to a, then a to infinity. Okay, 0 to a to infinity. In this time period, time after t equal to a, that means a to infinity range, e value is 0. So this term will be cancelled out. Okay, so that implies I bar equal into s ls plus r equal to e taken outside will be constant, 0 to a e to the minus st into dt, e to the minus st dt integration e to the minus st by minus s, 0 to a, just substituting the values, limiting values. Here a, it will be e to the minus sa by minus s minus e to the power 0 by minus s. So we found e into 1 by s, here minus minus plus 1 by s minus e to the minus sa by here minus s, minus is there, so minus a minus divided by s. So e multiplied e by s minus e by e into e to the minus sa by s. That implies I bar equal to this term is divided with this term and this term. We found e by s into ls plus r minus e into e to the s minus a by s into ls plus r. Let this is your equation number 3. Now we are going to apply inverse Laplace transform on equation number 3 we get. Here inverse Laplace transform this side will be applied, and also this will be operate or will be applied on these two terms, this one and this one. Now first we are going to consider Laplace transform of this one. Now consider first term of RHS of equation number 4. This is your equation number 4. This is the first term of RHS. First we are going to find out the Laplace transform of this one, inverse Laplace transform of this one. Then we are going to consider this one. So inverse Laplace transform of this one will be equal to inverse Laplace transform of E by, here you can see L taken common from these two terms will be Ls into S plus R by L. So here L and L. So E and L taken outside because constant. So E by L inverse Laplace transform of 1 by S into S plus R by L. Okay. Okay. E by L inverse Laplace transform of here. See this term somewhat modified as like this: L by R into 1 by S minus 1 by S plus R by L. You just add it. It will be the numerator will be S plus R by L minus S. Minus S will be got cancel R by L. Then we can found R by L. So L got cancel, and R also will be got cancel, and finally we can found 1 by S into S plus R by L. So this 1 by S plus 1 by S into S plus R by L can be written as L by R into 1 by S minus 1 by S plus R by L. Okay, so here L got cancel, E by R inverse Laplace transform 1 by S minus 1 by S plus R by L, right? Okay, so that implies inverse Laplace transform of this one, E by R is there, 1 by S inverse Laplace transform of 1 by S, because in Laplace transform of 1 we know that 1 by S, so inverse Laplace transform of 1 by S will be equal to 1. So 1 inverse Laplace transform of this one. So here you can see this is your S minus of minus R by L. That means this is in the form of S 1 by S minus A. That means the answer will be e to the power minus a, e to the at. The answer will be e to the at. So here a is your minus R by L. So inverse Laplace transform of 1 by S plus R by L will be equal to e to the minus R by L into t. Let this is your equation number 5. Now we are going to consider inverse Laplace transform of this one, which is important. Watch carefully. Here you can see, now consider second term of equation number 4. What we can get, what we can get, second term inverse Laplace transform of this one we want to find out, right? To solve the above second, so to solve the above, that means to solve this inverse Laplace transform, consider the second shifting property, whatever we have been already discussed. That second shifting property has been considered. So by second shifting property, just recall, if Laplace transform of f of t equal to capital F of s, then Laplace transform of f of t minus a, here t capital F of s, f of t minus a into unitary function u t minus a will be equal to e to the power minus as into f of s. Here f of s is nothing but Laplace transform of f of t. So if I am going to consider inverse Laplace transform of this one, then I can found this one. Inverse Laplace transform of e to the minus as into f of s will be equal to this one, f of t minus a into u t minus a. Okay, this is the second shifting property already we have been discussed. Now this second shifting property will be applied on this one. Here you can see, just to compare this term e into e to the minus s a by s into ls plus r. This is the second term. Second term. If see, this is the second term. This is the first term of LHS. If I will compare these two terms, the extra e to the power minus sa has been multiplied in your second term. See, here e by s into ls plus r. Here e by s into ls plus r. But here extra term e to the minus sa has been multiplied. Okay. So if you just compare this one with this one, that means f of s into e to the minus as. So what will the answer? Answer will be f of t minus a into ut minus a. So f of t minus a means the inverse Laplace transform of f of s, and inverse Laplace transform of f of s will be f of t, already we got, and there we have to consider f of t instead of t minus a. I'm going to show you. See here, e by s into ls plus r, inverse Laplace transform is this one. This is your the so-called f of t. Okay, that means inverse Laplace transform of this one, or we can say that Laplace transform of f of t is this one. Laplace transform of this one equal to this one, or inverse Laplace transform of this one equal to f of t, right? Now if I am going to multiply e to the power 80, e to the power 80 with this, okay, e to the power e to the minus 80 by using second shifting theorem, e to the minus as into f of s. Then if I am going to uh, uh, multiply here with this term e to the power minus sa, if I'll multiply e to the minus sa, then the answer will be how much? Not f of t, but the answer will be f of t minus a into ut minus a. Carefully you have to watch. See, whenever we have e by s into ls plus r, its inverse Laplace transform, we got this one, which is the so-called f of t, small f of t. Okay, or in Laplace transform of this f of t is this one, right? So if another factor e to the minus sa is going to be multiplied with this, according to second shifting theorem, see this is also can be written as capital F of s. Okay, then according to second shifting theorem, here e to the minus as into f of s, corresponding f of t will be f of t minus a into u t minus a. So here f of t will be f of t minus a. That means here t minus a into u t minus a. So fourth term whatever we, sorry, second term of the fourth equation, whatever we have, it is multiplied with e to the power minus sa. Okay, so inverse Laplace transform of this term, this one, is nothing but this into e to the minus sa, right? Inverse Laplace transform of this one already we found. How much? Already we found is your e to the power, sorry, e by r into 1 minus e to the power minus r by l into t. So whenever e to the minus sa is going to be multiplied, the answer will be whatever the f of t we found, that will be f of t minus a multiplied with ut minus a. So answer will be e by r into 1 minus e to the power minus r by l into t minus a into ut minus a. Here ut minus a belongs to unitary function. Okay, let this is your equation number 6. Now I'm going to erase it. Okay, so using second shifting theorem, we found the inverse Laplace transform of this one. Okay, so that is your equation number 6. Now equation number 4 will be using equation number 5 and 6. Equation number 5 is this one, inverse Laplace transform of first term. Equation number 6 is your second term. Here we have to just substitute. Here this value will be I equal to just this one minus this one, e by r into 1 minus e to the minus r by l into t minus e by r into 1 minus e to the minus r by l into t minus a into ut minus a. Now consider the ut minus a. If we are going to consider ut minus a, that means ut minus a will be equal to 0 in between 0 to a, and will be equal to 1 greater than a, t greater than a, that we know. This is the representation of a unitary step function or unit function. So graphically also this is this one, that up to a 0 to a value is 0, and above a this is 1, right? So now consider the time in between 0 to a. Time in between 0 to a, that means the key has been closed for a time that is your 0 to a. U t minus a value is what? 0. So this is the general solution of I. So for this condition, u t minus a will be 0. So this factor will be 0, I will be this one, right? Now, whenever we are going to consider t greater than a, t greater than a means circuit is in the open state. Open state means u t minus a will be 1. So the answer will be, here you can see, hmm, at t greater than a. Okay, so here you can see E by R into 1 plus E by R into 1 minus, both will be cancelled. E by R into this term plus E by R into this term minus E by R into e to the power minus R by L into t plus E by R into e to the minus R by L into t minus a. So this will be the solution for the LR circuit when uh, up to t equal to a time the key is closed and then opened. This is the solution. When key has been closed for a short time period, that means up to t equal to a, the solution will be this one. Okay, so thank you so much for watching this video. In our next class we are going to discuss about RC circuit. Okay, so thank you so much. Thank you.